The interpretation of the National Electrical Code sections 250.134b is accurate, which allows for an equipment grounding conductor, or EG, to be run outside of a raceway, provided it runs with the circuit conductors. In this specific scenario, this permits securing the EGC to the exterior of the feeder conduit using tie wraps. Employing this method of running the EGC on the conduit's exterior offers a viable approach to resolve the concern regarding the conduit EGC reliability. It is crucial, however, to ensure adherence to NEC requirements for both the sizing and installation of the EGC. The electrical code outlines specific requirements for equipment grounding conductors. These requirements are designed to ensure electrical safety and the proper functioning of electrical systems. The NEC Section 250.118 lists acceptable equipment grounding conductors. These include metal raceways such as electrical metallic tubing, or IMT, intermediate metal conduit, or IMC, and rigid metal conduit, or RMC. These metallic conduits themselves can serve as the EGC, providing a continuous lower impedance path for fault current to return to the source. The NEC Section 250.134 provides guidance on methods of equipment grounding. Specifically, 250.134b addresses the grounding of equipment connected by permanent wiring. This section mandates that such equipment be grounded by an EGC contained within the same raceway, cable, or otherwise run with the circuit conductors. The phrase "otherwise run with" allows for some flexibility in how the EGC is installed. It acknowledges that in some situations, it may be impractical or impossible to install the EGC inside the same raceway or cable as the circuit conductors. In such cases, the EGC can be run alongside the circuit conductors as long as it is physically close to them. The rationale behind this requirement is to minimize impedance. When the EGC is run close to the circuit conductors, the impedance of the grounding path is reduced, which helps to ensure that fault currents can quickly and effectively return to the source, tripping the overcurrent protective device such as a circuit breaker or fuse. This rapid clearing of the fault is essential for preventing electrical shock and minimizing damage to equipment. There are several factors to consider when deciding whether to run the EGC inside or outside the raceway. Firstly, consider the type of raceway. If the raceway is made of metal, it can serve as the EGC. In this case, there is no need to run a separate EGC inside the raceway. However, if the raceway is made of non-conductive material such as PVC, a separate EGC must be installed. Secondly, consider the size of the raceway. If the raceway is already full, it may be difficult to add an additional conductor for the EGC. In this case, running the EGC outside the raceway may be the only practical option. Thirdly, consider the environment. In harsh environments such as those with corrosive chemicals or extreme temperatures, it may be preferable to run the EGC inside the raceway to protect it from damage. Fourthly, consider the specific requirements of the electrical code. In some cases, the electrical code may require the EGC to be run inside the raceway. For example, in healthcare facilities, the electrical code typically requires all EGC to be run inside the raceway to minimize the risk of electrical shock. When running the EGC outside the raceway, it is important to ensure that it is properly sized and installed. The size of the EGC must be sufficient to carry the maximum fault current that could occur in the circuit. The EGC must also be securely fastened to the raceway and to the equipment being grounded. The NEC provides tables for determining the minimum size of EGC based on the rating of the overcurrent protective device protecting the circuit. For instance, NEC Table 250.122 provides guidance on sizing EGC for various circuit ampacities. It is crucial to consult this table to ensure the EGC is adequately sized to handle potential fault currents. In the specific scenario presented, where there is concern about the reliability of the conduit EGC due to the remote possibility of separation, running a separate EGC secured to the exterior of the conduit offers a reasonable solution. The existing conduit, if made of metals such as EMT, IMC, or RMC, is already an acceptable EGC per NEC 250.118. Adding a supplemental EGC provides an extra layer of protection and addresses the owner's concerns. When installing the supplemental EGC on the exterior of the conduit, it is essential to follow best practices to ensure its effectiveness and longevity. Firstly, ensure the EGC is properly sized according to NEC Table 250.122 based on the overcurrent protection device for the feeder. Secondly, use appropriate connectors and fasteners listed for grounding and bonding purposes. These connectors should be compatible with both the EGC material, typically copper, and the conduit material. Thirdly, securely attach the EGC to the conduit at regular intervals using tie wraps or other suitable fasteners. The spacing between fasteners should be sufficient to prevent the EGC from sagging or becoming damaged. Fourthly, protect the EGC from physical damage, especially in areas where it may be exposed to vehicular traffic or other hazards. This may involve using a protective covering or routing the EGC in a less vulnerable location. Fifthly, ensure that the EGC is properly terminated at both ends. At the source, it should be connected to the grounding busbar in the generator room. At the assisted living facility, it should be connected to the grounding busbar in the manual transfer switch enclosure. All connections should be clean and tight and should be made using appropriate connectors. Several other NEC sections are relevant to equipment grounding and bonding. Firstly, NEC 250.4 outlines general requirements for grounding and bonding, emphasizing the need for a low-impedance ground fault current path. Secondly, NEC 250.64 covers grounding electrode conductor installation, addressing how the conductor that connects the grounding electrode to the grounding system should be installed and protected. Thirdly, NEC 250.92 deals with bonding of metal enclosures containing service conductors, ensuring that these enclosures are properly bonded to provide a safe path for fault current. Fourthly, NEC 300.3 addresses conductors of different systems in the same raceway cable or enclosure. It is important to be aware of these sections and how they relate to equipment grounding and bonding. In addition to the NEC requirements, it is also important to follow local electrical codes and regulations. Local codes may have additional requirements or restrictions that must be followed. It is always best to consult with a qualified electrical inspector or engineer to ensure that the electrical installation complies with all applicable codes and regulations. Considering a scenario, imagine a 480-volt, three-phase system feeding a motor. The motor is protected by a 50-amp circuit breaker. According to NEC Table 250.122, the minimum size EGC for a 50-amp circuit is number 10 AWG copper. If the motor is located 100 feet from the electrical panel, the EGC must be at least 10 AWG copper for the entire length of the run. If the conduit is made of metal and is properly installed, it can serve as the EGC. However, if there is concern about the reliability of the conduit, a separate 10 AWG copper EGC can be run inside or outside the conduit. If the EGC is run outside the conduit, it must be secured to the conduit at regular intervals and protected from physical damage. Another scenario involves a lighting circuit in a commercial building. The lighting circuit is a 120-volt, 20-amp circuit. According to NEC Table 250.122, the minimum size EGC for a 20-amp circuit is number 12 AWG copper. If the lighting fixtures are located 50 feet from the electrical panel, the EGC must be at least 12 AWG copper for the entire length of the run. If the conduit is made of non-conductive material, such as PVC, a separate 12 AWG copper EGC must be installed inside the conduit. The EGC must be connected to the metal enclosure of each lighting fixture. In the context of a hospital and assisted living facility, maintaining a reliable grounding system is paramount for patient safety and equipment protection. Hospitals and healthcare facilities have stringent requirements for electrical safety due to the presence of sensitive medical equipment and vulnerable patients. The NEC Article 517 specifically addresses healthcare facilities and provides additional requirements for grounding and bonding. These requirements are designed to minimize the risk of electrical shock and ensure the proper functioning of medical equipment. In addition to the NEC requirements, healthcare facilities often have their own internal policies and procedures for electrical safety. These policies may include regular inspections of the electrical system, training for staff on electrical safety, and the use of ground fault circuit interrupters, or GFCIs, in wet locations. Furthermore, the selection of appropriate materials for the EGC and its installation is crucial. Copper is the most common material for EGC due to its excellent conductivity and corrosion resistance. However, aluminum EGC are also permitted in some cases, provided they are properly sized and installed. The connectors used to terminate the EGC must be compatible with the EGC material and must be listed for grounding and bonding purposes. The installation of the EGC should be performed by qualified electrical personnel who are familiar with the NEC requirements and best practices for equipment grounding and bonding. The installation should be inspected and tested to ensure that it meets all applicable codes and regulations. Regular maintenance and testing of the grounding system are also essential to ensure its continued effectiveness. This includes visually inspecting the EGC for damage or corrosion and testing the impedance of the grounding path to ensure that it is within acceptable limits. The use of appropriate tools and equipment is also important for ensuring a safe and effective installation. This includes using a calibrated multimeter to measure voltage and current, a ground resistance tester to measure the impedance of the grounding path, and insulated tools to protect against electrical shock. In summary, running an EGC on the exterior of the conduit is an acceptable solution to address concerns about the reliability of the conduit EGC, provided that it is properly sized, installed, and maintained in accordance with NEC requirements and best practices. The decision to run the EGC inside or outside the conduit should be based on a careful assessment of the specific circumstances and the applicable codes and regulations. Always consult with qualified electrical personnel to ensure a safe and compliant installation. Furthermore, documenting the installation is crucial. Keep records of the EGC size, material, routing, and connections. This documentation can be helpful for future maintenance and troubleshooting. It can also be used to demonstrate compliance with the NEC and other applicable codes and regulations. Finally, remember that electrical safety is everyone's responsibility. By following the NEC requirements and best practices for equipment grounding and bonding, it is possible to create a safe and reliable electrical system that protects people and property from the hazards of electricity. Consider the broader implications of grounding and bonding in electrical systems. Grounding and bonding are not just about preventing electrical shock. They also play a critical role in protecting sensitive electronic equipment from damage due to voltage surges and other electrical disturbances. A properly grounded and bonded electrical system can help to reduce noise and interference, improve the performance of electronic equipment, and extend its lifespan. In addition to the safety and performance benefits, proper grounding and bonding can also help to reduce the risk of fire. Electrical fires are often caused by arcing faults, which occur when electricity jumps from one conductor to another. A properly grounded and bonded electrical system provides a low impedance path for fault current to return to the source, which helps to quickly trip the overcurrent protective device and prevent a fire. In conclusion, grounding and bonding are essential components of a safe and reliable electrical system. They protect people from electrical shock, protect equipment from damage, reduce noise and interference, and prevent fires. By following the NEC requirements and best practices for grounding and bonding, it is possible to create an electrical system that is both safe and efficient. Remember to always prioritize safety when working with electricity. If you are not comfortable working with electricity, it is best to consult with a qualified electrician. Electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from harm.